So today we'll speak about descent directions, which is what we're trying to do is minimize the function without constraints. The function is continuous and differentiable and so on, whatever you want, but it's not convex necessarily. So we don't know that there's one minimum, okay, a unique minimum. But what we're trying to do is we're trying to find the direction in which the function is going down, so that we can proceed and create like an algorithm that, and there's going to be different types of algorithm, but we're going to create an algorithm that will get us to at least a local minimum. Okay? Maybe not the global minimum, but the local minimum. So we are interested in f from Rn to R, okay? And we are interested in minimizing it. And all we are interested in today is finding a direction in which the function is going down, is descending. It's a descending direction, that's what we're interested in. Okay? So
you can reach a local minimum, right?
Yeah, of course. Yes. And there's, you know, this is a very rich subject. We'll talk about it in stages. And you'll see how we handle a local minima. Maybe we can find in advance all the possible local minimas. Okay? And maybe once we get to a local minima, we can jump out of that area in some way to start the search again and different things. Okay? But all we're interested in today is finding a descent direction and then connecting it to one of the main techniques that we use in optimization to find a minimum. Okay? So let D be any direction, and we want to find a descent direction, one that goes down. So we can look at this function, which is any point in that direction, and we calculate f at that point. Alpha is a scalar. Okay. So that's a function. This is a function from R to R, right? Function of alpha. Okay. Now, so we want to find. We want that function we will differentiate that function, okay, in order to find a point where it's descending, and that will be a descent direction. Okay, so all we need is that the differentiation of this function at the point x0 is going to be derivative. The derivative of this function at the point x0 is going to be negative. That's all we're looking for. So what's the derivative of this function? So this function is a composition of two functions. So we need to use this rule here, okay? So what we're going to get is that the derivative of this function is the gradient, and we multiply it scalar multiplication with direction. Okay, so why? Because the derivative of f is the gradient, okay, and the derivative of this function
is d.
Is d. Okay, so it's exactly this rule. We're just applying it. So that's the derivative of this function. Mm-hmm. Now, if this is not zero, then in order for the function to go down, the derivative should be negative, right? So here's our first condition. So we want this to be. This is a condition for a descent direction. direction in which we're going down. Now, in addition to that, if we take this specific a vector, which is if the gradient is going this way, this vector is going to go this way. So if this is the gradient, this is our new direction, then the scalar and assuming the gradient doesn't go to 0 at the point, then this direction, if we multiply it with the gradient, where we are assigning it here, this is what we're going to get, right? Because the scalar multiplication.
Where did this equation come from? Why does d equal minus of the derivative?
I'm just taking a direction, any direction.
Oh, you're defining d as...
Yeah, I'm taking a direction. So, and that's going to be the game. Like, the Newton method will take a different direction. This is the steepest descent method. We're taking every direction will be part, choosing a direction will be part of the game of creating an optimization technique. So the minus goes out, and the scalar multiplication of a vector is its norm, right? To the square of 2. Okay? Now, this is a positive quantity.
d is a degree of freedom, right? You can't choose it.
Yeah, you can choose anything.
F is not. F is dependent on the function you are analyzing.
Yeah, the gradient is determined by the function.
Okay.
So the gradient is a function of the function. But I can choose minus the gradient.
Okay.
And that gives me one of the methods, basically. So in this case, if at the point the gradient doesn't vanish, then this is negative. So it's a descent direction. So we're going down. So that's one of the ways to proceed is to take this direction, and that's actually the steepest descent methodology. Yeah.